We are now going to consider finding the limit without considering the graph. We are going to figure out algebraically how to find the limit as x approaches some number a of f of x. There are three things you need to remember. 1. Substitute in a. 2. Factor and cancel and redo part 1. 3. It's possible that the limit could be infinity, negative infinity, or does not exist. So to find the limit algebraically, at this point, it's a combination of substitution, factoring, and then substituting, and knowing what our possible answers can be. First example, we'll consider the limit as x approaches 2 of x squared minus 4x plus 1. Well, I can substitute 2 into this, and I'll find that I get 4 minus 8 plus 1, which is negative 3. So the limit as x approaches 2 of x squared minus 4x plus 1 is negative 3. Let's consider a different problem. Something like the limit as x approaches negative 2, this time of the rational function 2x minus 6 over x minus 2. Again, I can find this limit by substitution. If I plug in negative 2, we'll have negative 4 minus 6 over negative 4. And this reduces to positive 5 halves. So the limit of this function is 5 halves. Our next example is a little different. The idea is still the same, we just run into a problem. The limit as x approaches negative 2 of x squared minus 2x minus 8. Ideally, we could just substitute in negative 2. In this case, though, when we do that, we end up with 4 plus 4 minus 8 in the numerator, and 4 minus 4 in the denominator, which simplifies down to 0 over 0. Now 0 over 0 is something called an indeterminate form. It just means if we arrive at something of this form, we can't determine anything about the limit. It may exist, it may not exist, but 0 over 0 simply means we can't tell what's going on based on our work. This is an indeterminate form. So, and we may have noticed this from the beginning, and if you do notice it at the beginning, it's always worthwhile to do, that the numerator of this function happens to factor, and it factors into x minus 4 times x plus 2, and the denominator of this function factors into x minus 2 times x plus 2. And when we simplify our function, we're still looking at the limit as x approaches negative 2, but we've divided out the x plus 2, and we're left with x minus 4 over x minus 2. Notice in my work, since I have yet to substitute in negative 2, I've kept a notation that I intend to find the limit as x approaches negative 2. But in my next step, now that I substitute, I've actually, when I've plugged negative 2 in, I've done what I needed to do in terms of finding the limit. I end up with negative 6 over negative 4. Notice the notation, the limit as x approaches negative 2 is gone. and I'm left with 3/2. So until you substitute in your finding limit process, you must keep the notation there, declaring your intention. The limit in this case is 3/2. Last example, we'll consider the limit as x approaches 1 of x squared minus 2x plus 1 over x cubed minus 1. Now you might consider substituting 1 in initially, and that's fine. I'm going to factor just to begin with, because I can see this does factor. The numerator factors into x minus 1 times x minus 1. The denominator is difference of cubes, and difference of cubes, this one will factor into x minus 1 times x squared plus x plus 1. Let me remind you, I'll do it up here in red, that difference of cubes always factors, so something a cubed minus b cubed always factors into a minus b times a squared plus ab plus b squared, and that sum of cubes factors as well into something very similar, in this case a plus b times a squared minus ab plus b squared. It would be valuable to have that as just a known fact, particularly in terms of factoring. In terms of my limit work, I'm left with taking the limit as x approaches 1 of, will that be x minus 1 over x squared plus x plus 1, and when I substitute in 1, I end up with 0 over 3, where the limit is 0. If I can't do much by plugging in a, and factoring and canceling doesn't help, then my answer is either infinity, negative infinity, or does not exist. Let's consider what we know here. To one that won't work out so well, and anything in particular won't work out. Let's consider the limit as x approaches 2 of 2x plus 5 over x minus 2. If we do the first step, we end up with 9 over 0. That's no good. It doesn't help. Cannot divide by 0. This doesn't factor, so step 2 doesn't help. So what I know at this point is that my answer is either infinity, negative infinity, or it does not exist. I can't really make any conclusions based on what I know. It's going to be one of these. I'm going to consider example number 8. Let's look at the limit as x approaches 2 of 2x minus 4 over x cubed minus 6x squared plus 12x minus 8. If I attempt to solve this by substitution, I end up with 0 in the numerator, and my denominator is 8 minus 24 plus 24 minus 8, which is 0 over 0, and this is an indeterminate form. Perhaps this factors, and I can see that my numerator will factor into 2 times x minus 2. My denominator, I can factor this, it looks like, maybe by grouping. Hard to say what's going to happen here. Well, if it's going to factor into anything helpful, it'll have to factor into x minus 2, and I'm going to use some synthetic division to help out. So I know that I want one of the factors to be x minus 2, because if x minus 2 is going to work, I'll do long division instead, that's the only thing that will divide out. So if I do long division, I've got x minus 2 going into x cubed minus 6x squared plus 12x minus 8. X times x squared is x cubed, and when I multiply x squared by x, I get x cubed. X squared times negative 2 is negative 2x squared, and now when I subtract, I'm left with negative 4x squared plus 12x. X times negative 4x is negative 4x squared, so I have negative 4x squared plus 8x, and when I subtract, I'm left with 4x minus 8. It's going to work. X times 4 is 4x, so I would get 4x minus 8, and when I subtract, I get 0. So this tells me that my denominator factors into x minus 2 times x squared minus 4x plus 4. Notice I didn't actually need to know how to factor it, I just needed to know what I wanted it to factor into. This helps me simplify this into the limit as x approaches 2 of 2 over x squared minus 4x plus 4. And now when I substitute, I have 2 over 4 minus 8 plus 4, and I'm left with 2 over 0, which doesn't allow me to conclude anything. And so all I can conclude at this point is that this limit is either infinity, negative infinity, or does not exist. It's one of those three. Finally, let's consider the piecewise function in example 10. Piecewise functions just means that there's two different rules that are governing the entirety of this function. In this case, we have one rule that applies after x is greater than or equal to 2. So we're going to use this rule, x over x minus 2, when x is greater than or equal to 2. And we're going to use x minus 3 over x minus 2 when x is less than 2. And what we'd like to find is, what's the limit as x approaches 2 of f of x? Well, in this case, the only thing I can look at is what are the left and right hand limits. And substitution is not going to help me very much in either one of these cases, because I can't actually substitute 2 in. And since substitution won't help me, I might attempt to factor or cancel things out, which happens in neither part of this piecewise function. And so I'm left with, I can conclude the limit will either be infinity, negative infinity, or does not exist. And you might look at the graph of these pieces to help you recognize that our reasoning is good and true. The final thing we need to consider today and in this section is the idea of the limit as x approaches infinity. Of some function. This idea is directly related to horizontal asymptotes. In fact, this is the definition of what a horizontal asymptote is. What's happening as x gets very, very large, approaches infinity, or very, very negative, approaches negative infinity. Now, if you'll recall from Algebra 2, there's only 3 cases. Whenever you see the limit as x approaches infinity, you should immediately be thinking about horizontal asymptotes, and there's only three cases. The first case, if the degree of the denominator is greater than the degree of the numerator. And in this case, when the degree of the denominator is larger than the limit as x approaches infinity of the function is 0. And the horizontal asymptote would be y equals 0. Second fact, if the degree of the denominator is less than the degree of the numerator. Well, this means that the limit as x approaches infinity of f of x is either positive or negative infinity. It's just going to continue. The numerator is going to get bigger and bigger, faster and faster than the denominator. It's going to overwhelm it. And then the third option is that the degrees are the same. The degree of the denominator equals the degree of the numerator. In that case, it's just the ratio of the leading coefficients. So for example, if we were considering the limit as x approaches infinity of 4x squared over 3x squared, they both are degree 2, so the limit is the ratio of the coefficients. In this case, it's 4/3. Let's consider another example along these lines. Let's consider the limit. This will be example 13. As x approaches infinity, so I see that, and I'm already considering there's only 3 possible things here. 4x cubed minus 5x squared plus 3x minus 1 over 5x cubed minus 7x minus 25. The degrees are the same, so the limit in this case is the ratio of the leading coefficients, or 4/5. So there we have horizontal asymptotes, which are directly related to the limit as x approaches infinity or negative infinity.